Well, here is another helpful example I've provided to try to give you some more additional guidance for how to do problems. And I wasn't sure if I had given you enough of an example, or if the problem I had given you was way too much harder than the one in the examples, right? So that happens a lot, where the homework is way harder than the example. So I figured I'd try to remedy that and make a really hard example that's pretty similar to what you're doing. So I'm hoping that will set you up for success, but maybe you've tried it and you've been frustrated already. So now that this video will probably try to help you. Now, like I had said in the previous video, there are really two different kinds of problems in this class. Cantilever beams, the door handles, and simply supported beams, which are the 3D shafts. The problem I gave you is not a 3D shaft. It is actually just a 2D shaft. So it's very, very similar to this problem right here. So we had Dr. Orlip and I adapted this problem, or one very much like it. I think we were doing this together. Maybe it was just me. I can't remember. So anyway, here is a problem that I'm going to go through, and it is very much like your homework problem. The very first thing I do in a lot of problems is to get some geometry things out of the way, right? So did I do them up above? I'm not sure where I did them. Yes, I did. Okay. All I need for 3D, I don't need the area, because I'm not going to do axial. So I say that I is equal to pi over 64 d fourth, and the diameter that we use is 1.5, which is pretty darn large. And that ends up with 0.2485 inches fourth. And then J is just equal to 2 times I. So that's going to end up being 0.4970 inches fourth. One thing in this particular thing that they like to do this a lot of times is say, we were given these two forces right here, but then they told us on the other side that the looser side is 25% of the tight side. All that means is that we would say, when taking a look at this thing, we're going to have to reason our way out through what the unknown, the missing tensions are going to be. And the best way to do that is to look down the axes. Now I'm trying to see how I did that. Okay, so what I decided to do is to look down the x-axis. But actually, I'd kind of going backwards than I usually would go. I usually would go look down the positive axis. But because of the way this is set up, I decided to look at it down that way. Most of the time, I would look at this way right here. It would be the standard view. But creepy eye, let's give him some eyelashes, is looking down in the same direction as the x-axis, as opposed to looking down the x-axis. So anyway, I want to draw this thing out. And the little guy is going to be right here, and we're going to have this. So this is an FBD, right? And putting on the loads onto the thing, on the big guy, this is known, right? That tension and this tension is known. In fact, let's FA1, this is 2,000 pounds, and this guy is 250 pounds. Now, which direction is this thing going to turn, right? It's going to turn to counterclockwise, obviously, right? So bear that in mind. Now go ahead and let's go purple here. We'll draw this guy in here and this guy, and this is FB1 and this is FB2. But which one's going to be more, FB1 or FB2? Well, you could just reason the thing out. It's in equilibrium, so the FB1 and FB2 better act in such a way to try to move it clockwise. Otherwise, it would be increasing speed. If this 2, the result of FBs was counterclockwise, it would just start speeding up, because these things are in equilibrium, running at constant speed, so they have to balance out. So our conclusion is that FB1 has to be greater than FB2. And therefore, the way this thing is stated right here, that means that FB2 is equal to 0.25 FB1, right? So the loose side is 25% of the tight side, right? If we were going to be really 100% correct in our FBD, we would also put reactions right here, but those reactions are actually showing up at both of the what do you call them? I'm losing my mind. Both of the bearings. So I don't necessarily want to give it a letter or a name, but this is in the YZ direction. So this would be RZ and this would be RY. But they're superimposed on top of each other, just for completeness. So to be able to solve this, we take the sum of the moments about the x-axis, and honestly, we should probably make it clockwise now, right? Would be the right-hand rule thing, but I think I probably did it here. Yeah, I did it with counterclockwise. Okay, so I say that 2,000, and I could do this, and I could do shortcuts on this, but I didn't here. 2,000 times the radius of A, which is 11 diameter, right? So it's 11 over 2, and then we have negative 250 because it's going clockwise, and it too is going to be 11 over 2. We could just take the difference between 2,000 and 250, multiply by 11 by 2, but we didn't. And then we take and look, and we go negative FB1, which you don't know, but it's going to be the radius of B, which yeah, wait a minute. Did I just say that wrong? Oh yeah, okay. I was a happy accident that this happened to be 11 and that was 11. So it was actually the diameter right here that happened to be there. Okay, so this should be 7 over 2, right? This diameter right here. I need to be careful when I say stuff. And then we take a look and we go, okay, well, the FB2 is going to be counterclockwise, but we already know that it's going to be 0.25 times FB1, and its radius is 7 over 2. And these happen to balance out, right? So what we find is that FB1 now is going to be equal to 3,667 pounds. And so we should get FB2 immediately after that of 0.25 times 3,667. And so we end up with 400. Look, I can't read my own writing. I think that says it's that must be 916. That can't be 416. So 916.7 pounds. And by the way, we're going to want to know at some point what FB1 plus FB2 is. Just so you know, we will want to know that. So I decided to calculate that for some reason down here. And that's 4,583 pounds. Another diagram we want to create while we're still here. We're going to want to know what the torque is. In order to know the torque, we have to cut the shaft. We have to cut the shaft because we can't. Right now, the torques balance out. The only way that they won't balance out is if we look inside and look for the internal loads. So that's something that people get wrong all the time. So I'm not just waiting for you to get wrong and then mark it off, but no, I will tell you. But at the same time, not everyone's going to watch this video. So the torque that's going to be on this shaft, which direction is going to go? Well, this pulley right here is trying to make it go counterclockwise. So that torque is going right here. It's inside the shaft. And by the way, if you were for completeness, we would also put in what the reactions are going to be right there onto the bearing that's on the other side that you can't see. But anyway, so we take the sum of the moments about the x-axis again, but this time we could do all this same stuff, right? It's going to be 2,000 times 11 over 2 minus 250, 11 over 2. But now we're going to have minus t equals 0. So we say that the torque we end up finding is 9,625 inch pounds, right? Okay, So we're going to need to know that, and its direction, I guess you could say that it matters, and we could start working through that if we want to when we get to a stress element, but we'll see in a second. So we have loaded up with the information that we need. So what we need to do now is create a free body diagram that's going to become a shear moment diagram. So we want to kind of set it up for that. And here we're going to be looking down onto this thing, right? So because you only need to do it in one plane. When we get to, we're going to do more 3D shaft stuff at times where you're going to actually have to see it in two planes and write out two separate free body diagram and shear moment diagram setups. And we'll see what the consequences of that is. Charging my phone, trying to talk and do it at the same time. So, we will go ahead and continue with this information over here. We'll set the thing up. And good to draw it out by scale. Make this one look a little bit bigger than the other one. Don't crowd the thing up too much. All right. And I label this. This is the x-axis. Let's take a look down here. The z-axis coming downwards. Z right here. We apply the loads at A, right? A, they're both coming this way right here. So that's just going to be FA1 plus FA2, right? They're seated on top of each other. We can do that in our heads. It's 2,000 plus 250, 2,250, right, pounds. Looking over here, they're going to be downwards in this view, right? And we already previously calculated what those out when we added those together. That's the FB, I'm just going to write down the number because there's a bunch of lines that are going to go down here. So that's going to be 4,583 pounds. The reactions on this are going... This is one of those, and I think your homework's the same way, where you don't quite know some of the directions. You could kind of forecast and guess. When in doubt, it might be best to just go in the positive direction. You know this one over here, which we're going to call ROZ, ROZ, right? Because it's at O in the Z direction. Over here, it's hard to say. So I call these a teeter-totter one, right? Where the forces aren't going in the right direction. So it actually aren't going in the same direction. So it actually depends on what these lengths are going to be. I'm going to call this one RCZ. And I actually, I guess I did forecast, and I happened to know that it was going to be this one's actually going to be in the opposite direction, and it kind of makes sense that it would be. So I'll backtrack on that and just say, yeah, but like you got to be careful that if you choose wrong and you get and you get a negative answer, that you're going to have to manage with the results of that. So. This is a shear moment diagram as well as an FBD. So I want to prepare for that, and I'm going to come down with lines over there. So I just don't want to start doing my work underneath this. I like to do it over to the side. So I say the sum of the moments about O is equal to 0 counterclockwise, and I start marching through. So I say that 2,000, okay, so first off, I see that the 2,250 is going to go counterclockwise, so that's 2,250, and the length of it is going to be A right here, this A, which was 11 inches, right? So, and by the way, sometimes it does help us when we're going through the thing, right? Make that 11 inches. Let's see, B was 17 inches, definitely not to scale, and C was 9 inches right there, right? Okay. So continuing on with what we were doing, this is going to be 11 inches. And then we take a look at the next one. Oh, this one, 4,583 is going clockwise, 4,583. and the distance to O is going to be 17 plus 11. So that was that 28. I actually can't do that kind of math in my head. And then lastly, we're going to have our CZ, and that is going to be in the counterclockwise direction as drawn. If we end up getting a negative number here, we know we did it wrong. So we have 11, so that should be 37, right? 11 plus 17 plus 9 is 37, and that equals 0. And if we get RCZ, we would do the math, and we end up, we get 2,800 pounds. Great. So it apparently was in the negative Z direction. And then we take the sum of the forces in the Z direction, equals 0, and downwards is positive for this. So we say that ROZ, ROZ, I like to say, we're going to go minus 2,250, and then we're going to go plus 4,583, and then we're going to go minus the reaction that we just got, and we say that ROZ is equal to 466.5. So not a whole lot. And it's coming down in that direction. So now what we're able to do our shear moment diagram, and we'll make our shear diagram. Boom, and why not try to make it horizontal? There you go, a little more. There's our V. Sometimes I will put in brackets the units. So we see that ROZ is downwards. Right here. I don't know why I'm messing with the colors, but let me go with the dark red. I like dark red. So that one is coming downwards, which is actually downwards is positive for us. That's very small compared to the others. So it's actually 466.5, and I will color it in, right? Make it a block. And then we go up 2,250. Boom, right? So it's considerably up higher. And so that's, we subtract 2,250 because this is technically the negative Z direction, and we end up with a negative 1,784. And then we go to add an additional positive 4,583, and what we're left with, or we better be left with, is our 2,800, right? Because this better make this thing go back to 0. Now, I didn't give myself enough room, so I got to extend my lines down a little bit, and I'll take my moment diagram. And when I go my moment diagram, what are we left with? Okay, we'll go with him. So my moment, and these are in inch, pounds. And as I start to look at this, I see, okay, well, I'm going to figure out what the area of that is. It's going to be 466.5 times 11. Sometimes I'll write that out over to the side. I don't require you to, but maybe it's a good practice. Maybe I should start doing it. But it's not going to be a whole lot, right? This is not a lot of area right here. But the area was 466.5 times 11, and that ended up with 5,132. I don't have to put the units because I put them over to the side. And now I want to get the area of this middle square up here. So I take 1,784 times 17, but it's a negative area. So I subtract, I guess. I subtract that out, and I end up coming way up, right? And still not to scale. And that ends up having a negative 25,200. And then I better check and see what my 2,800 times 9 are going to be. It better be equal to 25,200 so that we can come back down here with this positive area added to this thing. It better come back to 0 because these are simply supported and they can't sustain. So the max moment... And when we say max, we don't care about positive and negative moment. It's bending the thing. It's causing stress. It's causing both tension and compression. But is at B. Well, I said is at B. And so M max absolute is 25,200. So what we've done so far is we have gotten the loads. We got what the torque was, and we got what the moment was. So now we have two kinds of stress, and so we could start calculating them. And I might have to go to a different page, but let's see. So I go to my stress. By the way, I want to introduce this idea. Geometry, loads, stress. This is a procedure that shows up over and over again throughout the course. So just be on the lookout. So we say that we have axial, we have none, we don't need to even write it down. Bending, MC over I. We already got some of that stuff, the 25,200, what is the diameter was 1.5, right? So 1.5 over 2 is C. We already got the 0.2485 was going to be the moment of inertia. So we end up with, then I divide by 1,000 before I write the thing down. So 76.05 KSI, and it's tension or compression, right? Because it depends on which side of the shaft that you're looking at. Most of the time, we only concern ourselves with the tension side, because we'll find out in fatigue loading that a point on the shaft will actually rotate over and over again, and we'll go from tension to compression, tension to compression. But anyway, so the other one we have is we have torsion, and so that's tau is equal to TR over J, and we end up with that 9. What did we say? 9,000 or 9 point? Should be 9,000. I think my comma looks like a decimal point, right? So it's 9,625 times our 1.5 over 2 divided by our 0.4970, and that ends up being 14.52 KSI. So on a stress element, which is like the next thing we do, we would draw it this way right here. First off, if we were going to put a stress element, generally we don't need to put in an axis, but it's really along the X. And if we were really thinking about it in terms of our stresses, where it was going to show up, it would really be in the Y right here, right? Okay, so yeah, this one's fine. When we go to 3D shaft, we won't actually be able to do this, and I'll explain why. So that's good. We'll just draw the tension side, 76.05 KSI, or just 76.1 maybe. Keep it nice. And then the direction of this one. We can start arguing about the direction. We would need to think about this diagram right here and a stress element. And stress element would make, I believe, I drew it on my one here on my homework, and when I did a solution, I probably didn't give it much thought because it didn't really matter. I didn't think it was worth explaining, but you could start going through. So I'm not going to take off points. I wouldn't take off points for the direction of your shear stress on a stress element here, but I would on the door handle, because then it actually has a physical meaning that could be a lot more. But if you were going to try to work through what this would be, if you were looking at this side right here, right, that had this torsion that was being placed on it, and the stress element was right there, that would mean that it would be going upwards across that face, right? You could just as easily have, look at this side and have the stress element right here, but now the torsion's going the other direction, so it actually comes down that face. So you would end up with the same thing, right? So if it's on this side of the thing, it's going upward. On this one, it's going downwards. So on here, to do it correctly, it would be there and right there, and then now we got our partner ones, and so what you would end up with is our 14.5 KSI. So, and I don't think this year I asked you to do a principal stress on this, but I think I did that other year, and I think that was like too much work. But But anyway, this is it's a decent example to try to help you with what you have for homework, and hopefully someone will actually watch this and benefit from it, so that you can have a successful homework. Thank you and good night. My Saturday night for 25 minutes. Woohoo!